This week we're going to be discussing the mathematics and mathematical models used to describe interactions between populations of species. In particular, we will first discuss the interactions between a population of predators with a population of prey. This is the type of setting in which one of these populations serves as the food supply and a resource that is needed for the other species to survive. But before we rush off to start writing equations, I would like to guide you to several examples of predator-prey interactions. So on this slide here, you're gonna find some URLs with examples about the golden eagle versus the jackrabbit. This is a video by the National Geographic, and then you'll find other videos that also motivate these interactions. This week we are interested on interactions between two species, two populations, and specifically in the context in which one species serves as the food supply for another species. These type of interactions are usually known as predator-prey interactions. And before we continue, we're gonna take a look at a video that was made by the National Geographic, and this will serve as our motivation. Okay?
It is a king. The golden eagle, North America's largest raptor. This bird is an incredible hunting machine. A 7-foot wingspan, razor-sharp vision. Its eyes can spot prey from over 2 miles away. And a killer 150-mile-per-hour dive, which means this jackrabbit doesn't stand a chance. Jackrabbits are a favorite prey of golden eagles and a hopping pack of protein. The rabbit can run as fast as 40 miles an hour, but that's no match for talons that descend from above. The big bird has an incredible grip. It can squeeze over 750 pounds per square inch, so most prey are killed instantly. In addition to jackrabbits, the golden eagle mainly preys on other small mammals, reptiles, birds, fish, and even large insects. They're also known to eat carrion. These raptors are found all over the northern hemisphere and can live for almost 20 years in the wild. So if you're a jackrabbit, you might want to keep one eye and ear on the sky.
That video presentation can be accessed using this URL. If you'd like to replay it for better resolution and better sound, you're more than welcome to do so. There are other examples of predator-prey interactions, other videos that you can find in these URLs, and I invite you to pause this video at this time and visit each and every single one of these videos on your own computer, and before we continue this conversation. So let's take a pause. Let's now talk about the Hudson's Bay Company. The Hudson's Bay Company. If you visit the URL of this company, their homepage, this is what you will see. So let's just follow this link that tells us a little bit of information about this company. This company was founded in 1670. Okay, 1670. This company used to trade animal furs in Canada, and because they were well established in the trading business, they used to keep records of records that we're gonna see in just 1 minute. Basically, they had data for a specific period of time between 1848 and 1907, and they had observations or estimates on the numbers of two species, the population sizes on two species. So the Hudson Bay's company kept records on the numbers, estimated numbers on a population of Canadian lynx, also formerly known as Lynx canadiensis, and the population of snowshoe hare, formerly known as Lepus americanus. So if you have any doubt, the Canadian lynx was the predator that feeds or used to feed on the snowshoe hare. Okay, so what we're gonna see is, and what follows next, is a visualization of this data. It's an animation. These are year observations. These are records with estimates per year on the number of hares and the number of lynx in thousands. Okay, so we're gonna see a display as how each of these data points appears on a longitudinal sense. So as time progresses, then we will see the data points appearing. So this is how the graph of these observations looks like. We are going to have on the x-axis the time points. The time points have units of years. The first observation was collected in 1848. And on the vertical axis, the y-axis, we're going to have the numbers. So in 1848, there were 21,000 hares and 44,000 lynx. Okay, and we can see how the next observation comes on 1849, and we're gonna see how this progresses in time. So here we're gonna press play, and you can see the progression in time as the data points or the reports are coming in. So this will display observations every year from the year 1848 through 1907. So one thing to observe is that we can see some temporal patterns, right? And one thing I would like to observe is where each species attains, approximately where each species attains its maximum value. So we're looking there at the hares in 1857, around 1857, then the lynx in red, and then the hares get another large value in 1864, lynx in 1866. Then here's another maximum value of 1876, while lynx the 1876 also. The next peak seems to be in 1886, around 1886. Then 1896, 1895. And then 1906 and 1905. So what this is telling us is that we could have also looked for the points, the time points at which both curves are reaching a minimum level, but this is telling us that there is a pattern, in which numbers grow up to a maximum level, then they drop to a minimum level, and then they raise back to a maximum level. And this pattern seems to repeat. It's a pattern that has the signature of a cycle, and this cycle and the numbers of each species is something that is consistent in both the population of hares and the population of lynx. A very important point to make here is that the fluctuations, meaning by fluctuations, oscillations in population size, the fluctuations observed in the number of lynx seems to be correlated to the fact that the main food supply for lynx is hair. So when there is abundance of food, then the population that is feeding from that food seems to grow. However, when there is a shortage of food, when the food supply runs short, that seems to also have an impact on those predators that are feeding from that food supply, right? So this is a feature that is well observed in this type of data set. And this is a very well-known data set that is used as an example of the interactions between a species that is a predator feeding from a species that is a prey. So mathematical descriptions of these interactions between predators and prey are mathematical tools that they go way back. One of the pioneers in this type of challenge in using mathematical equations to come up with some description of these interactions is Vito Volterra. As you can see here, this is a copy of a paper that Volterra published in 1926 in the journal Nature. The original publication on what is considered today a prime model of predator and prey appeared and well, is noted here. Okay. Another person that's credited with describing, giving a mathematical description was Alfred Lotka, who almost at the same time was studying problems in a different context. What we will see next when we revisit these equations is that the terms that denote the interactions between predator and prey are terms that have something in common with the law of mass action in chemistry. So here is the first page of a publication by Lotka in the 1920s. This concludes our introduction to predator-prey dynamics.